Words on Water. Water. Element 6 is a global leader in the design, development, and production of synthetic diamond materials and is part of the De Beers Group. Since 1959, their focus has been on engineering the diamond synthesis process to enable innovative synthetic diamond solutions for a range of applications. Including machining, optics, and wastewater management, to mention just a few. As well as being the planet's hardest material, diamond's extreme and diverse properties give it high tensile strength, chemical inertness, broad optical transmission, and very high to solve a wide range of technical challenges. Learn more at www.e6.com.
Hi, welcome to Words on Water, a podcast from the Water Environment Federation. This is the host, Travis Loop. I am very excited for this. I am very excited for this episode today. I'm joined by Hossein Zarrin. He is head of water at Element 6, and I'm also joined by Tim Mollart. He is principal application engineer at Element 6. And let me tell you, Element 6 is a global and production of synthetic diamond and tungsten carbide and is part of the De Beers Group. They are here today to discuss how industrial synthetic diamonds are used to treat industrial wastewater. So this is a really new, interesting topic for us on the podcast. Hossein, thank you for coming on.
Thank you, Travis, for having us.
Absolutely. And Tim, thanks for joining as well.
Yeah, it's an absolute pleasure to be here.
Fantastic. So, like I said, I've talked about, I think this is very interesting for the audience. It's the idea of taking synthetic diamonds to treat water. Before we dive into how that works, could you just explain what a synthetic diamond is?
Well, the difference between synthetic diamond and gem diamonds in general is that the synthetic diamond is man-made. It's made, whether it's high temperature, high pressure, or chemical vapor deposition, it is man-made. So when I first told my wife I'm working with diamond to treat wastewater, she said, I want a ring with diamond. When I showed her the diamond that we're using, she said, no, I don't want this. I want the real one. So
you're still, yeah. I think as soon as you hear diamond, everyone's ears kind of perk up for sure. That's a great story.
So some people make abrasive, for cutting and drilling, but we use the diamond in a different way, and we manufacture it in a different way, which we will elaborate on that later on, and use the diamond for different applications.
Sure. As far as wastewater treatment, how can synthetic diamonds be used in wastewater treatment, and what type of pollutants can they treat?
Well, some industrial wastewater, they contain toxic chemicals that can poison biological processes. Advanced oxidation processes can treat these wastewaters. While the material science and electrochemistry behind this process is pretty complex, in its simplest form, we use electrical current to remove dissolved organic pollutants. Oxidation, and the electrodes are made of diamond. This is where the diamond comes in, okay? And in this process, there's no need for additional chemicals or high temperature, high pressure, or complex multi-stage processes. It is a simple oxidation technology. That can oxidize the pollutants and break them apart, basically. And it can be integrated in existing or new wastewater treatment plants.
And I believe this really has application water settings. Is that right,
Yeah.
Tim?
Perhaps I can add in there. I mean, as a society, we generate a lot of complex compounds these days, which are often designed deliberately to be resistant to digestion and environmental degradation. And some of those are known to become what's called persistent organic pollutants, or POPs. And in fact, I think in 2001 there was the Dirty Dozen was named in the Stockholm Convention on these. I'm left wondering how many times I can mention bad old movies in the podcast, but anyway, the Dirty Dozen were kind of were found, and it's things like PCBs, and it's easy to demonize some of these, things like DDT. People are trying to eliminate those in the environment, and new ones keep being found and added. So I think one that concerns the water industry these days, PFOS, or the kind of precursors behind the production of many fluorocarbons, that they're now on that Stockholm protocol. And really the thing is, and then many other things are stable enough to actually resist digestion and bioaccumulate in the environment. And it's things like painkillers. I believe ibuprofen is now considered so widespread is its production and its use that it finds its way into the water streams. And so these kind of recalcitrant dissolved organics, and that they're really designed to persist in the water, and they're not broken down by conventional digestive water treatments. And what you need a powerful oxidant such as the hydroxyl radical. And that breaks down these aromatic rings, these benzene rings, these phenol compounds, and it turns them just back into carbon dioxide. And in the wastewater world, these kind of hydroxyl radical processes, they're known as advanced oxidation. And as Hossein said earlier, the key thing about synthetic diamond is they enable a really simple electrochemical advanced oxidation process, and that's what can be built.
So what types of industries are most common for using this technology, for using the synthetic diamonds in treatment? Where is this finding its kind of niche?
So in-house treatment of low volume toxic effluents can benefit from this Diamox technology. This includes pharmaceutical plants, textile plants, chemical plants, and small refineries. Also multinational companies who want to apply universal best practice across multiple manufacturing sites, they can use this. For example, wastewater from pharmaceutical manufacturing sites often contains Tim mentioned, and they need to be removed before they're released, and they can benefit from this technology because it breaks up the molecules. Another example is the spent caustic from small refineries. This is refineries. This is really toxic material. They typically have high COD and contain chemicals that they are hazardous, inhibitory, or biorefractory. And electrooxidation processes can significantly reduce the COD toxicity. One more example is the removal of dyes from textile plants. Synthetic dyes have certain properties by design. They want it to be chemical resistant, they want it to be bacteria resistant, and they want it to be light resistant, so they don't fade or they don't change color during the life of the textile. And these pose a double jeopardy to the environment because they have aesthetic and toxicology problem. You probably have seen the blue dog on the internet, and blue rivers, red rivers, and green rivers. Those are the type of effluents that can benefit from our technology.
Interesting. I'm curious about how you make the conductive diamond. How's that happen?
Right. Well, I can perhaps answer this one. Industrial diamond's been around for about 70 years,
Okay.
and 70 years,
Okay.
and it's used for cutting, grinding, polishing, as Hossein mentioned earlier. And the main way that it's manufactured is this high temperature, high pressure process, which, if you like, mimics the conditions of the deep earth. You have to go about 100 miles down. Known method of making synthetic diamond, which is much more akin to kind of semiconductor manufacturing processes, which is called chemical vapor deposition, or CVD. And what you do with that is you take methane, and you take the carbon from methane, and then you grow diamond sheets, at low pressure, at low pressure, using a plasma that first of all strips the carbon from the hydrogen, and then uses that hydrogen to stabilize an atom by atom, layer by layer growth of a diamond crystal. And that's been perfected over the last 30 or so years, and to such a point now where we can actually grow those thin layers up into a piece of diamond, and then if you grow it on a sacrificial substrate, you can remove the substrate and you leave behind the layer of diamond that can be almost 6 inches in diameter thick. So you can certainly make sort of sheets of the stuff, and you can knock it around and use it. And then, of course, this is where sort of diamond gets interesting. Is that semiconductor process? Diamond, like silicon, it's a semiconductor, and we can dope it by substituting one of the carbon atoms while we're growing with boron. We can actually make it into a metal-like conductor material, and it retains all of those properties of diamondite. It's hard and it's chemically inert, and so that's what enables us to use it because it's simply inert enough that when you split up water, rather than forming oxygen straight away, you actually form the hydroxyl radical first, and then rather than digest the metal substrate, if you like, underneath, that hydroxyl radical sits on the surface for long enough for a molecule to pass over the surface of the electrode and be oxidized by it. So it's kind of and that's how we actually exploiting a semiconductor process, if you like, to make a synthetic diamond material that's used for treating wastewater.
Just some incredible deep chemistry at work here. That is incredible stuff. Why, Hossein, you mentioned some of the industry in this type of technology using synthetic diamonds in water treatment. Why aren't more industries or opting for this type of technology?
Well, Travis, everybody is cost conscious, and biological processes is certainly the inexpensive process. Technology such as biological pools, you wouldn't use this technology unless you have space problem and you want something compact, which we can offer that. But when the effluent contains toxic or biological, these biological pools or processes cannot be used. That's when we come into place. Okay. In many situations, a combination of both electrooxidation and biological process may be the most cost-effective process. We knock it down far enough that you can then feed it into the biological pool. We also are attractive to companies that they want, as I said, a small footprint with low odor, low noise. When this unit is on, there is no noise. It's like a light bulb. You turn it on, it oxidizes the water, and you can turn it off. and it's really that simple in practice. And plus, it's very stable. And its stability in mineralizing effluents and denaturing compounds in solution. This opens up potential for water reuse or recycle. So people who want to take the effluent out, but it's toxic enough you cannot reuse it, we can take that toxicity out, those organic compounds out, and then they can reuse it.
The innovation stand at WestTech, I think in 2017. And so to the water industry, I think we learned then with many of the groups that were there, we're very new technology in terms of the water industry. So we are still on the learning curve, or the early adoption phase with the technology. And as Hossein says, we have identified some real niches. And one of the great things about coming to WestTech has been the last few years that we've been able to build on some relationship and develop and work with partners who have developed unique treatment technology that does build. And also perhaps we're seeing that maybe you're going to see some regulations and stuff come into place. I think people are now really keen to do that. And certainly, say we come from Element 6, we're part of a large multinational, and we know that our company is keen to drive unilateral standards, across all of its operations across the globe. And so you are seeing large companies now push to perhaps this technology is now coming of age, and you'll see companies start to adopt it and roll it out across a multitude of sites, because it is this flexible, small footprint technology.
Well, it's great to hear that you've had that type of engagement at WestTech. That's what that big event is designed to do, is provide that interaction and learning. One of the things I wanted to ask about is how potential test this technology and see if it would work in their setting. How can they learn about, and evaluate your technology?
Well, our system is very scalable based on the area of diamond that we use and the current. You can scale it up or down. So we have 3 different sizes of reactors: laboratory size, pilot size, and production. And most of our customers, they do the feasibility and treatability study first, and then they make a pilot plant. And from pilot plant to production is very simple, because it is a modular system. You just add more modules next to each other, whether you want 2, 4, or 6, or whatever number of, based on the volume, flow rate, and contamination level, we can size the system. It's very linear. In terms of how they can test it, we do have systems for rental. We encourage our customers to use their own lab, because everybody has different analytical needs, and they know what they want, and from there they can move up. If there is an end user who cannot do the testing, we do have partners who work with, and they have testing facility, as long as they're willing to work with them towards a production size.
Great. Well, we know how fast technology is changing and how quickly science is advancing. You all are on the cutting edge of all of that. Where do you see cutting edge of all of that? Where do you see things going potentially in the future? How could you see this technology evolving and improving?
Some may say the future is here now. Electricity to do the treatment, and if we can get the electricity from solar panels or wind generators, they then the process is very green. It is very green. It is a sustainable process. If you don't have to purchase the electricity from electrical plants and that they use coal or fossil fuel. Mm. That's how I see it's being used. But right now, our first application really was in sanitization. Ozone, when it's used for electrolysis of water, it preferentially makes ozone. Mm. So when you use diamond electrodes, you can make ozone generators, and you can make miniature ozone generators. One of our customers has integrated this into a sanitizing spray bottle that turns regular water into ozonated water that is a very powerful sanitizing. And in this climate, you know how important that is. And you can actually buy the ozone spray bottle on Amazon today. And
wow.
Yeah, it is. It's product for our customer and for us. We are very happy to be a part of that product development.
Yeah. I can add that obviously I'm looking a little bit at WestTech at the moment, and I do see a lot about the trend towards online instrumentation and continuous monitoring, data management, and obviously I wonder whether there's an ability to combine some of that technology that's being developed now with kind of turnkey processes that you turn on and off to treat a point source of a recalcitrant effluent. You can imagine that it's quite an effluent. You can imagine that it's quite if the system can truly become online, this kind of technology lends itself to that because it's push button. It doesn't involve complex processes or chemical dosing. And then, as Hossein said, in these pandemic times, it's sanitization and sterilization, and perhaps we'll see something emerge that uses this technology in that direction rather than in the direction of water treatment, where it's looking to produce sanitizing capability and capacity. And again, that's something that really, I suppose, reflects the times we're in right now.
Yeah, very fascinating stuff for sure. Tim and Hossein, I appreciate your time and this information so much. And yeah, very, very illuminating, and appreciate it, and look forward to folks seeing you all as part of WestTech.
Thank you very much for having us, and it's been a pleasure speaking with you today.
Thank you very much, Travis. I agree. It's been really great.
Words on water.